All right, are we ready for some acid-base chemistry? Okay, so again, thank you for being here. At least I'm not facing a completely empty lecture hall. But getting started, we'll do some more or less review when we're talking about pH and pKa. We'll make some link between pH, pKa to the chemical equilibrium we discussed before. And then for the rest of today's lecture, we'll be talking about how do we predict acidity or basicity based on just molecular structures. And also we want to introduce a new concept called Lewis acid base. All right, so that's a general introduction in what we will be covering today. We saw some acid base in our previous lecture when we talked about reaction mechanism. So remember when we were doing arrow pushing, what we're doing is talking about how does the electron flow in the process of chemical reactions. So we did this example together in class. Just want to do it with you again here. So for example, the first reaction is the dissociation of a polar covalent bond in the HCl molecule. Our chlorine is more electron negative. Hydrogen is more electron positive. So dissociation of this covalent bond is electrons moving from the chemical bond to chlorine atom, and we end up with a hydrogen plus or proton and chlorine minus. So that's dissociation of hydrochloric acid. It's also dissociation of a polar covalent bond. And you should be able to know how to use arrow pushing to show the reaction mechanism of that process. Likewise, you can have hydrochloric acid reacting with OH minus. So what we have here is, again, when you're drawing the arrow, you start from the electron-rich part. So we have the OH grabbing that hydrogen, and we're dissociating the HCl bond at the same time. So this elementary reaction is called a substitution reaction. The way we're talking about is we're making a new chemical bond, a new OH bond, and at the same time we're breaking the HCl bonds. And using the arrow pushing to show that process, that's one of my expectations of you. And at the end, we have this pair. Both of them are neutral species. Aluminum chloride is neutral, yes. But at the same time, you can imagine your aluminum has some partial positive charge on it because of the electronegativity of the chlorine bonded to it. Or what we say is my aluminum can act as an electrophile. Later, we'll also see aluminum chloride here also act as a Lewis acid or electron pair acceptor. It is electron deficient. And on the right-hand side, we have NH3 with the lone pair or an electron pair donor. So that's our nucleophile. And the arrow pushing here is from the electron pair to that electron deficient aluminum in making a new bond here. We also want to add the formal charge on the final structure to make sure they're complete. So these are just very quick review on what we discussed about when we were doing arrow pushing reaction mechanism. And they're just inherently related to acid-base chemistry. And we will see acid-base chemistry a lot in organic chemistry as well. So let's get started looking at some of the fundamentals. Bronsted acid-base. So this is the most classical acid-base reaction you can think about. So when we say Bronsted acid, what we are saying is this acid is acting as a proton donor or a H plus donor, if you may. And a Bronsted base, on the other hand, is acting as a proton acceptor. All right, so that's the Bronsted definition of acid and base. So a typical acid-base reaction following the Bronsted definition of acid-base is say now we have HCl. We put HCl into water. And what we get is H3O plus and chlorine minus. So that's the same type of arrow pushing we were doing. We're breaking the HCl bond. We're transferring the proton from the HCl into my water. So if you think about this process, my HCl is the acid, and that is our proton donor. And water here is our base in this reaction, or my proton acceptor. Some of the, and that's on the reactant side. You have acid reacting with a base. On the product side, we have conjugate acid of the base. So H3O plus, that's a conjugate base of H2O. And chlorine minus, on the other hand, that's a conjugate acid. And chlorine minus, on the other hand, is a conjugate base of HCl. So the reactant side, we have acid base. On the product side, we have the conjugate acid and conjugate base pair. So that's one example here. Second example, you can also have neutral species acting as acid and base. Again, the definition of Bronsted acid-base here is just depending on which molecule is giving acid, which one of them is giving a proton. So your proton donor will be your acid in this case. So an example here is ammonia reacting with water, forming the ammonium cation and hydroxium anion, or NH4 plus and OH minus. So in this case, what we have is one proton is being transferred from water to ammonia. So now your water is acting as an acid or a proton donor. And your ammonia is acting as a base or proton acceptor. And the result here is, again, you can write the conjugate acid of NH3 to be NH4 plus. And then OH minus is the conjugate base of H2O. All right, so in this case, we always have conjugate acid pairing up with your base, conjugate base pairing up with your acid. So I expect you to know, say I give you some kind of acid, can you tell me what's the formula for its conjugate base? Or I give you a base, tell me what's the formula of its conjugate acid. So the process here is just a proton transfer. So some of the example question here is, let's say you have chloric acid, so HClO3, and its conjugate base, obviously it's losing a hydrogen, so the conjugate base will be chlorine O3 minus. Nitric acid, after losing that hydrogen, we have NO3 minus. And acidic acid, we're losing a hydrogen, and we end up with CH3 COO minus. All right, so know how to write the pair of acid and conjugate base, base and conjugate acid. Just in the general Bronsted acid-base reaction, we're talking about transferring protons between acid and base. So now, that's a qualitative understanding of the Bronsted acid-base concept. If we look at these two reactions, we'll soon find out that depends on what kind of other parts of reactant you have. For example, in this case, water here. When water is reacting with hydrochloric acid, it's acting as a base. And when water is reacting with ammonium, it's acting as an acid. So what determines whether or not your substrate is acting as an acid or a base? How do you decide the equilibrium position based on our understanding of these molecules? So we have quantitative ways to understand that process, and that's, we want to introduce pH and pKa. Or this should act as a review. I mean, to be honest, I'm assuming you learned that in 14A and B, so let's just refresh your memory in pKa and pH concepts here. So these are equilibrium in acid-base reaction. Before we jump into the actual acid-base reaction, let's just look at pure water. Imagine that you have two water molecules, and then in some condition, you end up forming a H3O plus and OH minus. So in this case, the reaction we're showing here is water is acting as both an acid and also a base. H3O plus is a conjugate acid of water. OH minus is a conjugate base of water. So here, people define that Kw to be H3O plus concentration times the OH minus concentration at 25 degrees Celsius. And the Kw can be measured to be 10 to the negative 14 mole square liter per liter square. And we know that in this reaction, your acid and base is always in a 1-to-1 ratio, so we can derive that the concentration of H3O plus and concentration of OH minus is always 10 to the negative 7 mole per liter. And that introduced the definition of pH. So when we're talking about pH, what we have is negative log of concentration of H3O plus. So if we're talking about pure water, we know that the H3O plus has concentration of 10 to the negative 7. So naturally, we have pH equals to negative log of 10 to the negative 7, which gives you the value of 7. So that's why we say 7 is our neutral pH. That's the pH of pure water. All right. So based on the concept of pH, apparently we can do calculation in converting concentration of the acid to pH of a solution. So for example, we can have one quick example doing it together. Let's assuming we know HCl dissociate in water in full. Can we calculate the pH of the HCl solution when we know like 0.73 gram of HCl dissolve in water to form 100 milliliter of solution? Right, so the way we're doing it is we know the equation we're using is this pH equation. So pH equals to negative log of concentration of water. And we can calculate the concentration of H plus, and then we can calculate the concentration of H plus or H3O plus. It doesn't really matter which one you use, they're the same idea. That equals to concentration of HCl. Your HCl is a monomeric acid, only dissociate one hydrogen per molecule of HCl. And do that calculation, we have a total of 0.73 grams divided by its molecular weight, which is 35.5 plus 1. That's the molecular weight of HCl, gram per mole, and times 0.1 liter. That's the 100 milliliter we have. I always write out unit. You don't have to do it, but writing out unit is a nice sanity check in you're getting the correct equation set up. And the concentration, we can calculate it to be something around 0.2 mole per liter. You plug this number back into the equation above, and we end up to be negative logarithm of 0.2 which is about 1.61. All right, so even if the concentration of your hydrochloric acid looks small, it's just less than 1 gram of HCl dissolving in about 100 milliliters of water, your pH is still really strong. And that's why we say HCl is a very strong acid. So this part is a logarithm scale. So even a little bit of concentration of your strong acid, you have high concentration of H+, leading to a very acidic solution. So that's HCl, that's just a strong acid. When we're talking about different type of acids, we have a way to quantify their acidity. So the idea here is using pKa and Ka to quantify the acidity of specific species. So again, this is a generalized acid-base reaction. Again, sorry. This is the first time we see this generalized acid dissociation or acid reaction. So HA, that's a general form of some kind of acid. It reacts with water, so water here is acting as our base. And what we're forming is the conjugate acid of H2O. And the conjugate base of HA. So that's what those 4 terms mean. Based on our understanding of equilibrium constant, we know that equilibrium constant, the big K, is given by the concentration of your product divided by the concentration of your reactant. And in here, the concentration of water is a constant. All right, so this is the equilibrium constant. And I want to pause here a little bit and just think about it. You look at the equilibrium constant here. On the top of the equilibrium constant, you have the concentration of H+, you have the concentration of A-, and on the bottom, you have HA and a constant. So you often hear the term of the stability of the conjugate base tells you the acidity of your acid. So that's the reason behind why we care about the stability of the conjugate base lies within this equation. In the equilibrium constant here, if my conjugate base is more stable, it means I'll have a larger equilibrium constant, or my reaction is more tilted toward the right-hand side, towards more dissociation of your acid. All right, so when we were talking about the acidity of a specific acid, HA, it's the same thing as we were saying. The conjugate base, A- here, is more stable. And the reason is with more stable A-, we have larger equilibrium constant, and that larger equilibrium constant would push my reaction towards the right-hand side to make the reaction more favorable towards the product. All right, so that's a quick connection to our previous topic on kinetic and equilibrium of chemistry. So back to acid-base. In acid-base, now we have equilibrium constant for this generalized reaction. And we know in this process, the concentration of H2O is a constant. So people develop new values like Ka. So Ka is defined to be equilibrium constant times this concentration of H2O, which is a constant. And when we end up with Ka to be on the right-hand side, you have the proton concentration, you have A-, the concentration of your conjugate base, and on the bottom, you have concentration of your acid. And pKa is being defined as a negative log of Ka. All right, so without doing any calculation, we will do some calculation together, but without doing any calculation, let's look at chemical insight into pKa. What does pKa actually tell you? So let's just think it through. If we have a smaller pKa. What it means is we have a larger Ka value. So this part of the logic is just based on the mathematical equation of pKa equals to negative logarithm of Ka. And then what we have is Ka, by definition, equals to H3O plus times A minus divided by HA. So what a larger Ka tells us is we have higher H3O plus in this reaction. So smaller pKa, we're talking about this substrate is more likely to dissociate higher number of proton into the solution, or this substrate is more acidic. So smaller pKa, more acidic. And here's the general walkthrough in why that's the case. All right, so let's look at two examples here in using the pKa equations. First example, we did that before, as water reacting with hydrochloric acid. It's a strong acid. We're dissociating into H3O plus and Cl minus. So you can check the table, you can Google it if you like. What we can find out is the pKa of HCl is about negative 8.0. And then the pKa of H3O plus is about negative 1.7. So what it tells us, smaller pKa, stronger acid. So on the left-hand side, we have HCl to be our stronger acid. And what that tells us is the equilibrium would tilt towards the product. Or to the right. And that is why when we draw the equilibrium arrow, the arrow leading to the product is longer than the arrow leading to the reactant. That's why we're saying the equilibrium is towards the product. Alternatively, you could also have a weak acid. So in this case, the example we're talking about is acetic acid, CH3COOH. So here the pKa of acetic acid is about 4.7. And we know the pKa of H3O plus is negative 1.7. So in this case, on the right-hand side, my H3O plus is actually a stronger acid. And the reason it is a stronger acid is because it has a smaller pKa value. So consequently, because on the right-hand side we have the stronger acid, my equilibrium now is towards the reactant. All right, so when you're talking about acid-base reaction, given the pKa value, you can tell which one of them is a stronger acid, and then you can draw the equilibrium arrow based on our observation. All right, I'll pause here for any questions before we jump into more organic topics. Yes?
Does that mean Cl minus is a more stable conjugate base than CH3COO minus?
So yes and no. The answer is, let's do not compare it between different reactions. What we can say here is H3O plus is a weaker acid, So Cl minus is a stronger conjugate base. It's a more stable conjugate base comparing to H2O as a base. So do not compare it across reactions. Question? Yes?
If HCl disassociates completely, wouldn't the Ka be like infinity?
Well, it depends on what we're talking about. So here, you can calculate the Ka depending on the concentration of your HCl. So it's not going to be infinity. It's something you can calculate. All right. So this one is a more quantitative picture of acid-base. We talk about definition of pH, definition of pKa, how they are calculated, how to use pKa. You'll see one of the questions in your discussion worksheet is now we know the connection between pKa, Ka, and also with equilibrium constant. Remember, with equilibrium constant, you can calculate the delta G of the reaction, right? So you can actually connect what we discussed today, the acid-base chemistry, back to the chemical equilibrium we discussed before. So I'll see that in your next week's discussion session. Continue our discussion. I mean, we're organic chemists. We start talking about organic chemistry, and one of the things in organic chemistry is you might not have the pKa table for all the substrates you want. So you want to have some general idea about whether or not which one of my hydrogen is more acidic, or in a complicated molecule, how can I identify or how can I predict whether or not it's acidic without checking the pKa table, because you might not have that table for, we do not have that pKa table for every organic substrate we have in mind. So back to this equation. Before we move on, I want to make sure we emphasized it. When we're talking about the acidity of a specific acid, in organic chemistry, generally what we are saying is, do we have a more stable conjugate base? So like what we said before, the stability of the conjugate base relates to the acidity by writing out the equilibrium constant, right? So my K equals to H3O plus times A minus divided by HA and H2O. So more stable conjugate base means you have larger equilibrium constant, and that tells you the equilibrium is more moved towards the right-hand side. Your acid is more likely to dissociate. So keep that in mind. Stronger acid, more stable conjugate base, and vice versa, more stable conjugate base, you have stronger acid. Well, we'll use that concept a lot, so keep that in your mind. All right. And from here, we'll see several factors that's contributing to the stability of your conjugate base and consequently to the acidity of your acids. So now we're talking about the stability of a conjugate base. Or in general, we're talking about the stability of an anionic species, if you may. So obviously, the first factor is our electronegativity. So recall the definition of electronegativity. More electronegative an atom is, like fluorine and oxygen are more electronegative, means they have stronger attraction to their valence shell electrons. What that means is, depending on the electronegativity, let's look at the trend of fluorine, oxygen, nitrogen, and carbon. So we're going from group 7 back to group 5, group 4. All right, so with the decrease of electronegativity, we have an increase in stability of the conjugate base. All right, so what we have is from fluorine to carbon, we have decrease in electronegativity. So consequently, we have a decrease in stability of the conjugate base. And as a result, we have an increase in acidity. So in this trend, HF is our most acidic acid, and CH4 is our least acidic acid. And the reason behind it is depending on the anionic species we're talking about. So the anion on fluorine is more stable comparing to the anion on oxygen, on nitrogen, and on carbon. All right, so the electronegativity factor, this one is a very strong factor. It generally works with only one exception. And we will see that exception when we talk about factor 4 here. There's only one exception that's within the halogen trend. So fluorine, chlorine, bromine, and iodine. There exists exception of the electronegativity trend. Other than that, this is one of our most powerful trends in determining the acidity of a specific molecule. So that's our first factor. Second factor, inductive effect. So now what we're talking about is imagining we have the anionic charge on the same atom. We're talking about all these OH groups. So all my acid is forming an oxygen-centered anion. And when we say inductive effect, what we're saying is instead of having an electron-negative atom or electron-withdrawing group like fluorine directly binded to the site that's being deprotonated, now you have fluorine atoms that's a little bit distant away. But even if when they're distant away, they can still withdraw electron density to themselves and stabilize the anionic charge that's being built up. So when we say inductive effect, two things. The first thing, you're comparing the anionic charge on the same atom. And secondly, we're talking about electron withdrawing group or electron negative group that's distant away from your anionic charge species. So the way to look at it is now imagine you have different kind of charge, but in this trend, you have different number of fluorine atoms. It's pretty distant away, but you have different number of electron withdrawing groups on those acids. So in this trend, what we have is the bottom ones are having more stable conjugate base. And the reason they are more stable conjugate base is because of the inductive effects. All right, and consequently, the bottom one will be more acidic. All right, so that's our factor number 2. Factor number 1 is generally speaking stronger. Factor number 2, this one is more like an additional factor. Now we're talking about the anionic species is on the same atom. All of them is on oxygen. And then we're talking about how does other groups on your molecule affect the stability of these conjugate base. So that's our factor number 2. Factor number 3, hybridization. So again, we're talking about the same anionic atom. It does not overrule your factor number 1. Hybridization might play along with your factor number 2. So in here, the hybridization concept is after deprotonation, now you have an anionic species. If your center atom, in this case carbon, if it has more S character, it means electrons are located closer to the nuclei. Or the other way to better remember it is if you have more S character in that hybridized atom, that atom is more electron negative. So your sp carbon is more electron negative comparing to your sp3 carbon. So in this case, the example we're talking about is ethane versus Yeah, I forgot the name there, but it's okay. That's why I'm not testing you on nomenclature. Anyway, so we're talking about the acid here. So we have sp3 carbon, sp2 carbon, and sp carbon. So when we say the hybridization is different, here you have the negative charge on the sp carbon. So the sp carbon has more s character. So it is more electron negative. So it attracts those anionic species closer to its shell. And in contrast, we have sp2 and sp3. So the acidity increase when the hybridization change. All right. So far we talked about 3 different factors. They normally just work with each other. The first factor, depending on what kind of anionic species you are forming, right? So O minus is more stable than N minus, than C minus, etc. Second rule, inductive effect. So now your electron withdrawing group is not directly bonded to your atom, rather it's somewhere distant apart. But you can count the number of electron negative group. For example, fluorine, more fluorine atom would have more inductive effects to stabilize your conjugate base. The third one, hybridization. So sp is more stabilizing your conjugate base comparing to sp3 because of the larger s character. And then factor number 4, size of the atom. So this one is more or less a special, we call it size of the atom. People sometimes also call it polarizability of the atom. So this pretty much just talking about the trend in group 7. So in this case, when we're going down the period from fluorine to chlorine to bromine to iodine, what we have is stronger acid. So in this trend, my HF is too small an atom, it's not polarizable. So it's the least acidic. Where on the right-hand side, my iodine is the biggest. So this is probably the only opportunity we overrule our factor 1, which is electronegativity. So this one is an exception. Unfortunately, this exception you do need to know. All right, so that's the first 4. Right now, they all look pretty straightforward, but lying in the heart of organic chemistry, we will jump into our 5th factor, which is related to resonance stability or resonance stabilization of your anionic charge and its effect on the acidity of a molecule. So we talk about that in organic chemistry a lot, and please pay more attention to drawing these resonance structures. Before we do that, just a quick reminder. More stable conjugate base means we have a stronger acid. So we talk about other factors, electronic factors, stabilizing the conjugate base, like electronegativity, inductive effects, or what we have the hybridization effects. On top of it, we also discuss resonance structure can stabilize your anionic species. Resonance structure can stabilize that negative charge by delocalizing it between different atoms. So resonance structure is a very strong tool in organic chemistry, deriving which hydrogen is more acidic. So let's look at some examples together. We'll use 2 different examples together, and then we'll do some practice problem together as well. First example, we have carboxylic acid versus alcohol. So judging by its name, you would expect the carboxylic acid to be more stable, to be more acidic comparing to alcohol. But why that is the case? So here, R just tell you it's any alkyl group, can be a methyl, ethyl, etc. So in this case, let's just, again, first, when we're talking about acidity of a molecule, we write out its conjugate base. So let's just do that. So the conjugate base of my carboxylic acid, we're losing that proton to form a conjugate base. On the right-hand side, similarly, we're losing a proton, and we have O-. Simply looking at it, both of them are oxygen-centered anionic species. Both of them do not experience hybridization differences, and they don't have very strong inductive factors around it. But the left structure have an additional layer of stabilization coming from resonance structure. So if we're doing arrow pushing, what we're having is the electron can move in this direction. So the anionic charge is now located in a different oxygen. And what we end up with is R O- on a different oxygen and double bonds on the bottom here. Where on the right-hand side, alternatively, you don't have that stabilizing resonance structure in play. So if we're comparing these two, the conjugate base of your carboxylic acid is stabilized by resonance structure. All right. Let's do another example together. Well, we'll just keep doing examples for the rest of today's lecture, and if you have questions, just raise your hand. Another pair of example is now both of them have the OH group. Both of them are alcohols. On the left-hand side, we have phenol, where you have a phenyl group connecting to that OH. On the right-hand side, we have ethanol. So likewise, let's draw their conjugate base. So lose a proton, your ethanol ends up to have a negative charge. And we do not have any resonance structure to stabilize it. Well, alternatively, on the phenol end, after deprotonating, what we end up with is this one. With a negative charge on the oxygen. And here we actually have all kinds of different ways to stabilize that negative charge throughout in my benzene ring. So let's do some arrow pushing together. So for example, we can have it here, attacking that carbon, and it can move around here. So what this arrow pushing is saying is electron on this oxygen is moving onto this carbon to form a double bond, but we can't have 5 bonds on this carbon. So this double bond needs to dissociate here to form a carbon-centered anionic species. So what we have is a neutral oxygen like that. You can further move that anionic species around throughout the ring to have other resonance structures. And we can move it one more time. All right, so it's just using the arrow to show how the electrons are moving and try to understand like why we're drawing these resonance structures like this. So apparently in this case, our phenol is being largely stabilized by all kinds of resonance structures. Are these three more stable than the left one? Not necessarily, but they exist and they do provide extra stabilization because your negative charge is. I'll stop on time. Okay, let's just stop it. I hear it every week. I'll stop on time. Anyway, so your phenol is being stable. The conjugate base of your phenol is being stabilized by resonance structure, and that is why your phenol is a stronger base. All right, so resonance structure lies in the very heart of organic chemistry, not just where you're drawing the Lewis-Dot diagram. Also plays a role in how your reactivity works and also plays a role in the acidity of your organic molecule. All right, so let's do one more example together. And then you can work on these practice yourself because these are just generalized practices. First of all, draw your conjugate base, and then show all the resonance structures with it. Okay, so let's do one example together. That's this one. So now when we're talking about drawing the conjugate base of this molecule, you actually have two different choices. You can either deprotonate a hydrogen from the terminal, or you can deprotonate a hydrogen from the internal position. And how do we get an idea which one of them is more acidic, or which one of these hydrogen will get deprotonated first? So the way to do it is you write out the resonance structure in both cases. Let's look at the blue case first. Deprotonation of that blue hydrogen would end up with a molecule like this. So I write out that hydrogen just a reminder that your carbons do have octets of electron. It's a carbonyl species. Obviously, this specific conjugate base is stabilized by multiple types of resonance structures, if you may. So it can either go this way, to form a stable resonance structure, or it can go this way to form a stable resonance structure. And both of these resonance structures should be pretty good because we have oxygen-centered anionic species. We have that negative charge on an electronegative compound. Let me change this to blue just to avoid confusion. All right. But alternatively, if we're deprotonating this terminal hydrogen, what we're getting is something like this. Again, likewise, a carbon-centered anionic species. It has one resonance structure in stabilizing it. So what we have is both structures are being stabilized by resonance, but this blue hydrogen gets way more stabilization because it has more ways to delocalize that negative charge. So what makes it, this hydrogen, to be a more acidic hydrogen? All right. The same logic also applies to other practice problems. So in these cases, again, what the question is asking you to identify the most acidic hydrogen in this molecule. Like in this case, for example, you have all kinds of hydrogen. You have sp3. Here, you have sp2. And then you have sp hydrogen. So the sp hydrogen is more acidic. It gets deprotonated first. So do these practice. You'll have more of these practice in your next week's discussion session as well. I don't have time to cover Lewis acid base. We'll pick up on our next lecture on Lewis acid and base. All right.